now. And thank you everybody for joining the NOAA AOML Physical Oceanography Division seminar series. Our speaker today is Dr. Hyun-Sook Kim, and she will be speaking to us about the three-way coupled HICOM HWAF WaveWatch 3 simulations of Hurricane Laura in 2020. So Hyun-Sook got her PhD in 1995 from the University of Rhode Island, and she has joined AOML as a oceanographer recently in November 2020, and before that she has worked for NOAA EMC in Maryland for many years on the interactions between the ocean and hurricanes. And so for people listening via GoToMeeting, please remember to mute your speakers, and for those in the audience, if you have a question, we'll try to use the microphones at the end of the presentation. Hyun-Sook, the floor is yours. Take it away.
Thank you, Matthew. Hello, everybody. And today's work is done in collaboration with the HWAF team at the EMC, Brandon Rittel at TFDL, and Alan Wardcraft at FSU. The motivation of this study is the following. Under moving TC, the generation of ocean surface gravity waves poses different levels of complexity in the ASC interaction zone than the ocean coupling alone. In the presence of gravity waves, airflow becomes rougher. Hence, these waves are more efficient in extracting momentum flux from the air. Besides, wave interactions with the winds and ocean currents become highly nonlinear in the TC fields, and it should be included in a numerical modeling. Okay, today's talk has 5 components. 1, introduction to the system and the coupling. 2, experiments for Hurricane Laura. 3, validations for TC, ocean, and the wave forecasts. 4, results and discussions, and finally, summary and conclusion. This slide shows a three-way coupling system, which I have built on the operational HWAP HICOM forecast system currently running for JPWC basins. And then we added the WaveWatch 3 with the variables, feedback variables highlighted in the shadow box here. Okay. And the role, I'm sorry. Adjust something. The role of the surface roughness is the modulation of the LC interaction processes and the fluxes, and the role of the Stokes drift from the WaveWatch 3 into the HICOM is to enhance Langmuir mixing, turbulence mixing to the KPP mixing in HWAP, and also add the Stokes and Coriolis forcing in the momentum equations. So it turns we can simulate the nonlinear wave and current interactions. So if we go more specific, LC flux estimates are using the prescribed CDCK shown in the bottom figures, which is as a function of the wind speed on axis and the value non-dimensional on the y-axis. These are based on the channels relationship shown in this equation, provides a surface roughness Z0 with a constant value, which is 0.185 for neutral conditions for channel coefficients. So depending on the C state, the value can be changed. I mean, it's fixed, but the Z0 is changing, fitting into this prescribed curve for current configurations. And this slide shows that one of the core part of the coupling, which is a wave boundary layer, is part of the WaveWatch 3 AC interaction modules. So on the right figure, it shows that the sort of schematic diagram how the WaveWatch 3 with the coupling works in the wave boundary layers. So surface roughness, which is not mainly dominated on this range over here. However, the wave velocity cannot resolve on this part. So one way to do it is to parameterize it, or using equivalent range model to prescribe the tail end of the spectrum. And then I am following the Moon et al. 2004 approach, which is based on the conservation of a momentum flux, and the second one is conservation of a wave energy. So within a wave boundary layer, WBL, the momentum flux is total momentum flux is the sum of turbulence flux plus wave-induced stress at the boundary layer, which is exactly the same as atmospheric momentum flux at the z equal to 10, or at the top layer of the surface boundary layer. And the second equation is the conservation of wave energy, which requires mean wind vectors. So this is wave turbulence kinetic energy equations try to find minimum mean wind vectors, which is logarithmic wind profiles within these boundary layers, so that they can continue iterate the processes. So in this Z0, this equilibrium ranges in order to we use the approach that Moon et al. Or Rachel 2014 has presented here. Okay. So this slide is a nonlinear interaction part of the system, and the one is wind and the currents interactions by adding surface currents into the momentum computation in the L side. So in other words, this momentum, atmospheric momentum flux is with respect to ocean currents. And the second one is waves and the current interactions. And there are two parts. One is the Stokes-Coriolis forcing into the Hyun momentum equations. And the second one is adding Langmuir mixing to enhance KPP mixing using the Langmuir enhancement shown in the bottom two lines, the second lines from the bottom. And then here, the Stokes-Coriolis forcings, we use the monochromatic waves for Stokes drift. So in other words, Hyun receives one wavelength, and then the total Stokes drift at the surface. We're projecting the Stokes drift at the surface into the vertical as a function of exponential decay with the depth, depending on the mean wavelength. This is the domain configuration and the three-way coupling. The shade and in gray, pink, and cyans are the H-warp triple nested domain. And the gray is a D1 outer domain, pink is D2, and the innermost one, D3. This pink and the cyan domains are following the stones every single instantaneous time. Whereas D1 outer domain is a sort of a quasi-geostrophic, quasi-static domain, but often it changes based depending on the storm locations. And the box, blue box and the red dashed lines are the static, Hyun, and the wave watch domain at the resolution of 9 and 11 kilometers respectively. And then H-warp, there are triple resolutions, and the ranges from 1.5 kilometers to 13.5 kilometers for outer domain. And this is experiment configuration. I do have a three-way coupling, which stands for which is H3W1, and I added two extra experiments which is H21 only, including atmospheric components. H21H is operational H-warp, two-way H-warp and high-com coupled system. And the bottom panel table shows that the model components with the initial and the boundary conditions for individual model components, and also have a data simulation approach where atmospheric uses hybrid ENKF, and the ocean HICOM is based on encoder-driven analysis restart file. So case study in Hurricane Laura in August 23 in the 2020, and it becomes a real, media went a buzz because there were two storms in the Caribbean and the Gulf of Mexico. Both are heading toward the Gulf of Mexico. And then unfortunately, Marco has a very strong shear in the Gulf of Mexico. It didn't have a chance to intensify until, except a brief moment after 64 knots. Whereas Laura, when she marches along toward the Gulf of Mexico, she's run into low shear environment and the warm Gulf of Mexico SSD. And at the time, the translation speed is a little bit medium range between 6.5 to 7.5 meters per second. And then this is, top panel shows that the OI SSD at the August 21st, and then the control lines is a 26 degree, and the hotspot on here is 32 degrees Celsius on here. And the superimposed and best track Laura and then Marco in a Saffir-Simpson wind color scale. And the bottom panel shows that the V maximum observed V maximum wind for Laura in orange and Marco in orange and Laura in blue. So one thing you notice that Laura went to rapid intensification as soon as she's entered into the Gulf of Mexico. So over the 56-hour period, the intensity changed from 50 to 130, so about 80 knots for the period, which is about translated into 32 knots of the 24 hours, which is belong to the rapid intensification criteria. And this slide shows that 27 verified cases for homogeneous comparison among three experiments. Black is H21A atmospheric, red in the two-way coupling, and then blues are three-way coupling. Track in A, and intensity, B maximum intensity on the B in mean absolute error. And the bottom panel C and D are scales for track on the left and the B maximum intensity on the right side. So overall, when you look at the track validation comparison, both two-way and the three-way coupling improved track quite a lot, especially at the 5-day 120-hour lead time and up to 40 nautical miles MAE reductions. So this particular time in the day 4 and day 5, the improvement is statistically significant. And the similar improvement is shown in the Vmax MAE on the B. And but the reduction is pretty much 7 knots and 2 knots with respect to 21A or two-way coupling respectively. However, the improvements are not statistically significant. Although I have not shown in the bias plots, but also shows three-way coupling improves the bias by 6 knots over atmospheric run, and 3 knots for over two-way coupling. As for scale, track, and the intensity, wave coupling has about the 28% and the 17% for track and intensity improvements over atmospheric alone. Extra 2 or 3% improvement over the two-way coupling. And this is one particular cycle that I'm going to focus on for the rest of my talk, which is typical for the almost the 12 cycles out of 27 verifiable cycles, and showing that track has improved by three-way coupling in the blue in the top panel against the best track in color shaded tracks over red in a two-way and the black in atmospheric simulations. And the bottom panel shows that the P minimum pressure, the dashed curves and the solid lines are the V maximum intensity for best track in a gray shade, and then all three experiments in the different colors. So what is shown in this particular B is that comparison of the RI, observed RI, which is 32 not over the 24 hours period, and the three-way coupling is very close to the observations. However, atmospheric is over intensifying and similar to two-way coupling. And the most importantly, there's a time lag. It's about almost 12 hours off with the atmospheric side experiments than the three-way coupling. So next slide is the wave validations. There are 32 NDBC buoys in the blue dots on this figure, but I looked at only two. This presentation slide presented two NDBC stations. One is at 42003, which is on the right side of the best track, and the 40119 on the left side of the track. And the middle one, which is 42002, is unfortunately malfunctioning during the LoRa passage period, or during the summer 2020, nonetheless. So what is shown here is a significant wave height HS, peak period PP, 10-meter wind, and the direction at the bottom panel. On the left one is NDBC buoy 42003 on the right side of the track, and the right panel shows that station at the left. And the observation in the black color and the simulation is in blue. So overall, there is a very consistently high correlations between observation and the simulations. And the magnitude of the agreement is pretty close. And this is a statistics for these two stations with the four different variables. And notice that this wind direction, statistics low correlations coefficient for wind direction at the station 42003 has to do with the mixing data in early first 25, 26 hours on this period. And this one is the glider observations that are used to verify the TNS ocean simulations. There were all total 14 gliders existing, and then over the Puerto Rico, there's mainly 10 LMLC gliders plus one Navy glider here. And then there are 3 gliders in the northern Gulf of Mexico. It's right near to the best track, LoRa storm passage. And there are 3 ones, NG3 Navy gliders, 3114 and 645, and the TMU Stormel, glider Stormel. Okay, so this is a little bit busy slide. This tailored diagram of the ocean metrics to evaluate the skill, ocean forecast skills. And the A was in pre-storm conditions, B is in storm cycles. I have 7 ocean metrics at different colors. Overall, and temperature is neutral between pre and in-storm conditions. However, large improvement in the S salinity for two-way coupling, which is shown in the dot, this solid dots. Okay, so red one is H21, and before and then during the storm. That's a great improvement by reducing standard deviation is almost 0.7. And the largest improvement is the mixed layer temperature, which is shown upper triangle here before storm, and during the storm is here. Okay, and then ocean heat content, which is diamond pre-storm and then in storm, and the T100 plus sign before and then during the storm. However, there are degradations, especially mixed layer depth and then mixed layer salinity. Okay, so mixed layer depth starts here and degrades in storm conditions. And the salinity lower triangle was here, but this is pretty much out of range. And during the storm, comparison between two-way and three-way coupling, two-way performs better with MLT, OHC, and then MLD. And then there are substantial degradation for MSL. Okay, why? And this one is a temperature and salinity transaction from the two Navy gliders, 314, 645 on the right side of the track and the left side of the track, and the temperature in the blue and the red, and the salinity in the green yellow on each side. The top panel is observations, middle panel is a two-way, and the bottom panel is three-way coupling over 120-hour forecast period. Dashed line is a mixed layer depth, and the solid line is a G26, 20-degree isotherm depth. And the vertical line is the location, timing of the close the distance to TC locations. So notice that, you know, there are less variations in storm response on the left side of the track, but on the right side, there are a lot of variations going on, especially, you know, near initial undulations in both in temperature and salinity. And then also salinity. And then one thing you notice that the salinity structure, upper salinity structures in the three-way coupling has a better simulation than the two-way coupling. It's close to the observations, having the main thermocline, main headline is close to the observations, whereas the H21H two-way coupling, the salinity after storm is pretty uniform. And then the degradation of salinity for three-way coupling comes in parts at the very low. It's almost 34.4 PSU existing from before storm comes in and start to mixing after storm perturbation. So this particular long has to do with the low salinity tone comes off from the northern Gulf of Mexico. So Erica Bauer, which is my intern, summer intern, is focused on these particular features. So interested, please join the her presentation. This is SST and the SST cooling validation using OI daily product. And the left panel is the temperature SST cooling of 6 days period, especially during the LoRa period. And notice that there are substantial cooling exists on the Gulf of Mexico. So that one goes up to 2.5 degrees Celsius. Overall, the temperature is the range of this particular area, especially on this best track, 30 kilometers east of the best track is ranges between 28.5 to 31.2 degrees. And this one is compares box plots of the three-way coupling in blue and the two-way coupling in red in the daily comparisons. observation is in a no color box plots on the edge. So day 0, 1, 2, 3, 4. And notice that the OI-SSD, the mean and or median values ranges about the 29.2 is pretty much constant next 5 days. Whereas three-way and the two-way coupling, they are decreasing in general of that same period. However, two-way coupling SSD is colder by almost 0.5 degree on average than two-way coupling. And the coldest, again, three-way coupling shows that the coldest temperature in the overall. And we need some data simulation needed to correct this cooling, especially at the day 0. And next one is, this is an example of a footprint SST and the SSD cooling from the three-way coupling on the top panel and the two-way coupling at the 54-hour forecast from the diesel cycle. And notice that there are substantial SSD differences. And then also you'll see the immediate cooling within 64 radius, 54 radius, and then 50 or 64 radius exist. And there are also cold wave existing in the same way. However, three-way coupling shows that has more cooling. Higher SSD cooling takes place is almost 3.4 overall max on the footprint. And then around the 54 knot radius, it's almost 3 degrees compared to three-way coupling today. Two-way coupling is a little bit warmer. But predicted intensity is opposite. And even though higher intensity is predicted H21H, but the cooling is less than 120 V maximum intensity from wave-watch 3. So this one mainly has to do with the nonlinear interaction with the waves and the current. This one slide shows the mixed layer depth, and then at the same forecast time with the three-way coupling from the on the top and two-way on the left. Left one is the instantaneous mixed layer depth simulations, and then this is a mixed layer depth changing from T equals 0. And the positive means the mixed layer depth gaining or deepening with the time. And notice that in a three-way coupling, the gaining or deepening of mixed layers all around on the footprint. Whereas two-way coupling is mainly located right side of the track, and the left side is less. On the right panel, figures shows that the footprint mean MLD of mean MLD on the footprint with the minimum and the maximum in the shade for three-way in the blue and the two-way in red. And the mean value, again, is almost 0.5 meters differences in a 500 kilometer radius. And then another thing, notice that is, during the intensification period, the maximum mixed layer depth for wave-watch three-way coupling is up to almost 90 meter depth, whereas two-way coupling goes up to 70 meters. So in other words, during the intensification, even the maximum prediction is less, the mixed layer depth is keep deepening, and then this is a good side in the aspect of the typically HICAM mixed layer depth is shallower. So this nonlinear also Langevin mixing in a correct typical shallow mixed layer predictions by HICAM. And this is ocean heat content, the same on the footprint of the same period, and there is no differences, the main ocean heat content between two-way and the three-way coupling. However, when you look at the OHC rate over 6-hour period, there are substantial differences and then very consistent pattern. Okay, and then I shaded the two regions, one in the green and then red. One in the green is when the storm is passing over the loop current. At that time, obviously, loop current provides a very high ocean heat content, but the wind is weak. But in the red shaded period, which is the rapid intensification period, the ocean heat content is almost, negligent. It's much less than 60 kilojoule per meter square. But on the other hand, there are large differences in over time. Okay. So there is different degrees of heat uptake. Is mainly has to do with some different mechanics. Okay, so I'm going to reserve this video for the next slide. That's the second, I'm sorry, that's the next slide. Okay, this was enthalpy fluxes from atmospheric side model simulation, two-way and the three-way coupling at every 3 hour in lead time on the y-axis, and then radial distance from 0 to 5 times of R max. Okay. What is shaded in this particular period is the storm goes pass of the loop current, and see that there are large significant flux changes of that period. Okay. And once the storm passes, during the rapid intensification, there are different degrees of the enthalpy flux increases. So again, atmospheric model alone, there is significant gaining of flux compared to three-way coupling. Okay, on the right side, the top panel on the right panel is the rate of the flux changes in time, and the bottom panel repeated ocean heat content. So when I look at the visual comparison, there is some similarities, okay, going on here. Okay, so I'm going to reserve, this one for further investigation. So enthalpy fluxes, I am again focusing on an 06Z on August 24 cycles, and then top on the right panel is time series of heat fluxes, footprint maximum value for different experiments. And this line curve is very similar to field maximum intensity curve. Okay, so you know that the enthalpy flux is linearly, related to a field maximum TC intensification. And then at the radial, the maximum intensity of fluxes is found the one radial maximum radius, and it's about almost 70% of maximum value of three-way coupling is 70% of the atmospheric coupling alone, or 82% of the two-way coupling. So overall, three-way coupling is provides less enthalpy fluxes. And the next two slides, I'm going to show that PBL and the storm structures. Top panel is atmospheric alone, middle one two-way, and the bottom is three-way coupling as a function of the radial distance and in x-axis and the lead time on y-axis. And the superimposed is the PBL height in 1 kilometer, 1.5 kilometer, and the 2 kilometer PBL height on a superimposed. So the PBL, obviously, at the atmospheric alone, H21A, it goes up to higher than 2.5 kilometer at almost the R max, 1 R max. And yet, three-way coupling goes up to almost 1.5 or 2 point something or 2 kilometer which is close to the 1.5 kilometer that Zhang et al. In the 2011 has shown. And that different definitions for PBL height, but the maximum height is coming from the mixed layer depth criteria. Okay. So again, Threeway coupling mitigates overshooting PBL height. And the next one is the storm structure. Shown here is tangential velocity in the shade and the radial velocity in the contour lines on the 42 forecast hour and the 54 forecast hour on the left and the right hand respectively. And notice that, H21A predicts very deep storm structures, and it started from early 42 in the middle of a rapid intensification period, especially on the data dipole and inflow outflow, just at the eye wall at the height of the PBL. And the similar structure exists with the three-way coupling, but almost 36 hours later, that this intensifies tremendously for H21A compared to H3W1. And then their outflows, it's very high. It's almost 2 meters per second at the drop of pose, whereas in a three-way coupling, it's almost 15 meters per second. And two-way coupling is in the middle between. And this one is scatter plots of the enthalpy fluxes on the x-axis and the PBL height on the y, and height and the different simulations. That for H21, red is a two-way coupling and the blue is a three-way coupling. And then Zhang et al. In the 2015 and 18, he mentioned that the PBL height is related to TC intensity, or maybe the other way around. There are many goes into it, but I also looking at the only PBL versus enthalpy fluxes from this study. And again, in the two-way and the three-way coupling is kept out of the PBL heights as well as enthalpy fluxes. So we don't know what the typical enthalpy flux value is in reality, but having a more complex LC interactions simulations, we reduces the maximum PBL heights as well as PBL heights. Okay, and then this is a discussion section. At the bottom panel is the footprint SSD at 30 forecast hour from the 06 August 24 at the atmospheric component experiments on the left, and the three-way coupling in the middle, and the two-way coupling on the right side. And the both two-way and the three-way coupling, I also superimposed the surface currents so that it shows a better loop current better. And the black lines is a predicted track, and all the contours, dash contours representing the different wind radii. And notice that SST for atmospheric run alone, there's no loop current whatsoever. Okay, and also that is temperature changes at very small. Whereas two-way and the three-way coupling, there are a lot of activities going on, interaction between wind and the loop currents, and then including waves. Okay, so which one is right is still on debate, but having a three-way extra degree of LC interaction process in the simulation, this is a future way to go, and then that's what we have to working on it. Okay, so conclusion is that stay away from non-coupling, which is especially using static SST or 1D ocean model for hurricane simulations. next ill representation of mid-scale eddies, especially on the Gulf of Mexico. And the three-way coupling, from the simulation, the wave height, it goes up to almost 12 meter or 13 meter, which is almost very high sea state conditions based on WMO code. So this is very important for shipping or recreational sea activities. So, and having this wave coupling is also a benefit for social society, as well as sea interaction inclusions, including sea spray, bubble, breaking waves, so on and so forth. And then this one, okay. In the three-way coupling study demonstrates sea state dependent CD, as shown on the left panel set of figures. And this is the Chen et al. 2013 papers. And the CD in the shades on the top panels for atmospheric alone, and the three-way coupling on the left side. In the higher red one is higher CD, and then blue one is a low CD. And then this CD is three-way coupling shows that there are substantial changes on the CD curve depending on storm quadrants. Okay, whereas atmospheric side is pretty linear. However, our simulations between 21A versus and the three-way coupling, the CD patterns are pretty similar. The differences. The reason is that HWAP is highly tuned to CD and CK bulk formula, which is in a cyan currently that I used. Okay, so all these data points are depend on the CD depending on the different state conditions. So imagine that all the sea states are very range quite a lot, even high wind or even low wind conditions. However, our HWAP CD curves is fitting into this particular shape, which is similar to what Chen has shown here. So having a three-way coupling in this particular prescribed use of particular CDCK, not much beneficial, except nonlinear interactions. Okay, summary and conclusions. Total 27 verifiable cycles for Hurricane Laura shows the track and the intensity improvements by reduction of 28 and 15% of MAE for track and intensity respectively over atmospheric alone, and extra 2 or 3% improvement over two-way coupling. And the three-way coupling shows the better RI simulations. And we also shown the wave and the ocean simulations verified against the observations, showing that their simulation skills are pretty decent. And the TC focused improvements mainly owed to the inclusion of nonlinear interactions in the three-way coupling. As I said, in a shift state role from the wave watch 3 is a minimum on this configuration. So further in the future, I like to utilize the wave coupling by getting away from the bulk function, but using directly estimate of the shift state roughness length scale from the three-way coupling. And this is interaction upcoming presentation, as I briefly mentioned in my talk. Erica Bauer, she will working on the precipitation and the freshwater barriers for Markland hurricane in 2020. This animation is immerged precipitation over that period from 21st August to 28th August. So definitely at this time, there are a lot of precipitation brings the Laura on this particular period. And then this is accumulated precipitation for Laura on the left and the marker. And there are hotspots. These are very interesting. And this particular hotspot on the Gulf of Mexico, again, Erica is gonna working on it. And thank you. This is the last questions.
Thank you very much, Hyun-Sook. That was a very interesting presentation.